Okay, so here's what we were talking about last time. We were talking about the chain rule, and this is the last version of the chain rule that we wrote down. If z is a function of a bunch of other, what we're going to call intermediate variables, I'm going to call them y1 through yn. If those y1 through yn are functions, each of them is a function of several other, input variables, x1 through xm. Notice that n and m do not have to be the same. Right? Then if you want to understand a partial derivative, such as the partial of z with respect to xi, note this is a partial derivative of the composition. Right? You can write that partial derivative in terms of the partials of sort of what I'll call the smaller partials, right? So the partials of z with respect to the y variables, and also in terms of the partials of y, the y's with respect to xi, in the usual way, right? It's still about paths and propagation of changes. So along that path, changes propagate as per that term, right? And then likewise for other paths, so along that path, changes propagate a la that term. And it's just a matter of just keeping track of all the different ways that changes in xi can propagate through and cause changes in z. Okay, all right. Oh, whoops, I hit the wrong button. I wanted to hit, there we go. Okay, so now we did an example of this last time. I'm not going to go through the example again. What I'd like to start with now is how to rewrite this equation in a different form. So I'm going to leave all of this colored as is, and let's go over here and look at a seemingly more complicated scenario. What if I want to talk about a bunch of output variables? With again a bunch of intermediate variables, again a bunch of sort of input variables. Again, therefore, in other words, having a composition. And suppose I'm interested in the partial of, and I'm going to say, let's say zp with respect to x1, whatever. Notice it's not really a new version of the problem. Altogether, how I understand how zp changes with respect to these variables is I just ignore those, right? I want to know how zp changes. If there are other functions of the y variables, okay, so what? It doesn't affect my question of how does specifically that one variable zp, how does that change? So really, it's this scenario all over again. One output variable. Same deal. Same equation. Okay, so let's talk about how to write that down. And let's, color choices. Okay, so blue is, okay, all right. So I'm going to understand that green partial derivative as, well, I need to look at a bunch of partials of zp with respect to y input variables, intermediate variables, and then I correspondingly need to look at a bunch of partials with respect to, we're looking at x1 here, of those intermediate y variables. And if you write that down, write down the same formula that we had on this previous page here, it turns out you can algebraically write this in a different way. I'm going to write it as something called a matrix product. How many people have seen matrix multiplication before? Show of hands. Okay, if you haven't, don't worry about it. I'll show you what you need to know for the purposes of Math 212 on matrix multiplication. It's just a matter of, there's a silly little rule. It looks kind of weird. Those of you who have seen matrix multiplication can probably confirm it's a weird looking rule. But anyway, here it is. Skip down real quick. If you want to talk about a particular element of a product matrix in the ith row and the jth column of the product matrix, all you do is you take the ith row of the left matrix and you dot it with the jth column of the right matrix. It's literally just a dot product. Corresponding row of the left, corresponding column of the right. Okay. So now let me show you how that would look then. I mean, what that makes this formula turn into in terms of matrix multiplication. Now keep in mind what this formula is. It's about paths. You have a bunch of terms that all look kind of like this, right? So partials of z with respect to the y's being multiplied by partials of y's with respect to whatever your input variable xi is. And notice matrix multiplication, if you write the matrices down in this form, that's what this is, right? So now, again, reminder, we're looking at the partial of zp with respect to x1. And let's suppose I call that the bottom left element of this matrix. The partial derivatives arranged in matrices according to the pattern that I have written down here. That partial derivative, that of the many partials of the z's with respect to x's that I might want to know, I might want to talk about, we're going to take the corresponding row of the left matrix, and we're going to dot that with the corresponding column of the right matrix. So matrix multiplication gives you, in fact, all of those terms, right? You look back at this formula, and multiplying, blue partials times yellow partials as arranged there, you just notice that it's, in fact, exactly this dot product. It's this dot that. Same formula. Right, so one term at a time, it's this times that, plus this times that, plus dot 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 this times that. It's the exact same algebra. Okay, so this is a very fortuitous, let's call it a coincidence, seemingly, right? The chain rule that we motivated by how changes propagate, looking at variables individually. That formula that we've written down there happens to be perfectly represented by matrix multiplication if you arrange the matrices this way. So this is worth capitalizing on. This is a huge convenience, as it turns out. And as such, we're going to give these matrices names, right? I'm going to say if you take the green partial derivatives, the partial derivatives of the composition, if you arrange them like this, I'm going to call this the Jacobian matrix, named after a mathematician, Jacobi. But the Jacobian matrix of that composition. And likewise, notice it's the exact same arrangement in looking at the blue, the partials of the z's with respect to the y's. That's the various partials of that blue function, arranged in exactly the same way. And likewise, this is the Jacobian of that yellow function. So specifically what I mean by, ordered in this way, notice that the rows of these matrices are gradient vectors. That row, looking at this first row of that matrix, that's all of the different partials of Z1. That's a gradient. That's the gradient of Z1. Kind of a coincidence, seemingly, right? Likewise, this is the gradient of the function ZP as a function of the y variables. Likewise, this is the gradient of the y1 function. This is the gradient of the yn function. This is the gradient of the z1 function composition thought of as a function of the x variables, etc. So rows are gradients. And then in further good fortune, columns are partial derivatives. Here we're taking the partials with respect to x1. So that column is a partial derivative. It's a partial derivative of, all the z functions with respect to x1, a single input variable x1. And likewise, this is the xm partial, and these are the y1 partials, etc. Okay, so this arranging a bunch of partial derivatives in this way, we call this a Jacobian matrix, and it gives us this wonderful sort of shorthand then for the chain rule. All of these formulas, great, big, huge, monstrous, inconvenient formulas that go all the way across the page, right? of which there are many, right? Because there are many different partial derivatives that I could conceivably be interested in. This is a tremendously awkward way to write all of those partial derivatives. Tons of huge formulas. And they're all compactified in this extremely compact and elegant reformulation as, Jacobian matrices multiply. Look how compact. It's crazy compact. Everybody on board? Like I say, this is a big win in terms of, elegance, convenience of writing down the chain rule. So I want to encourage you all to think about the chain rule in different ways. There are situations where this point of view on the chain rule is really nice. Thinking about intermediate variables giving rise to separate terms. It's a very cool way to think about the chain rule. In different circumstances, this is just way better. In some circumstances. Okay. All right, so let me show you some examples. Here's one. Now, this is just an example. Correction, this is going to start off as just an example. All right. Let's consider where I have a composition. Okay. Specifically, I want to consider where the first domain, the first input space is R1, specifically, R1. And I want to just write down the chain rule. Let's write down this version of the chain rule. In other words, products of Jacobian matrices. And here you go. This is it. Right? We're going to think about the partials of the composition. Well, in fact, those aren't even partials. Those are just derivatives. There's only one input variable, after all. And that those derivatives of the composition are, let's see here. We're going to have, if you will, the blue partials, Jacobian matrix, times the yellow. I'm going to say partials, but wait a minute. There's only one input variable to that yellow function, so those are actually derivatives. Right? So this is just a for example. This is what the chain rule looks like when your sort of leftmost domain has only one input variable. And then you notice, well, hey, if I were to conceive of t as being, the one input variable, if I were to think of that one input variable, let's call it t and think of it as time. Notice what I've got here, these derivatives that I've got here in yellow and green, those are the derivatives of, in fact, a couple of parametric curves, right? That's a parametric curve through Rn. That yellow function, parametric curve through Rn. Position is a function of time. It's a parametric curve. Which makes this not just a derivative, but it makes this actually a velocity. That's a velocity in Rn. And now let's look at this composition. Now we have y variables in Rm as functions of time. That means that this green derivative, this is a velocity of a parametric curve in Rm. And as such, that gives us a very nice alternative interpretation of the Jacobian matrix. Keep in mind, we're looking at the blue function here, whose derivative is this Jacobian matrix. That Jacobian matrix of this function I'm calling G here, that Jacobian matrix is a relationship between input velocity and output velocity. And here we are again, right? Now, so going back to first day that we were talking about derivatives, and I had my cornerstone foundational point of view that I want to take on derivatives is that derivatives are relationships between input changes and output changes. And check it out, this Jacobian is doing that. This Jacobian is a relationship between input velocities and output velocities. Just like a derivative ought to be, right? So this is I believe, a very compelling argument in favor of interpreting this Jacobian matrix as being fundamentally the derivative. I mean, if you had to pick a thing to be the derivative of that G function, well, this blue matrix is, as far as that blue function is concerned, this is the relationship between input velocities and output velocities. That's what a derivative is. So this is a really important point of view to take on multivariable derivatives. The derivative of a multivariable function is a matrix that relates input velocities to output velocities in this way. Okay. All right, and here's a sort of a picture. I forget the colors. I said yellow and green. Yeah, so here's that input velocity. That's the derivative, aka the velocity of the first parametric curve. Here's that output velocity, derivative of that composition parametric curve. Oh, did I do I did the color wrong. Sorry, this is green. Green. All right, so input velocity, output velocity. Those velocities are related by the derivative, aka the Jacobian matrix, the derivative of that function g. Okay, so different ways you can look at this statement. Again, you can think of this as a statement of the chain rule. I mean, after all, that's where this came from. This algebra that I wrote down was just a special case example of this matrix form of the chain rule. But you can also view this as a reinterpretation of what is a derivative. A derivative is a matrix. So I want you to take it in both senses. Both senses are really important. Okay. All right. And now let's reinterpret again. Just another sort of look what you could do sort of point of view. Let's think about a composition again. So yellow function, blue function, right? The yellow function being a function from the x's to the y's. The blue function being a function from the y's to the z's. Now notice I'm no longer thinking of my initial domain here as being just time. Right now I have a composition of arbitrary multivariable functions. And I'm just going to point out that, but reinterpreting Jacobians as relationships between input velocities and output velocities. The thing that you do to turn an input velocity into an output velocity gives us a really nice alternative point of view on the chain rule. And it goes as follows. The yellow Jacobian is the thing that allows you to translate that input velocity into that output velocity. That turns x prime into y prime, if you will. Here, let me write it like this. The thing that turns that into that. Right, well, likewise, the blue Jacobian, the Jacobian of that f function, that's what turns the y velocity into the z velocity. Right? And, well, then, in fact, furthermore, the Jacobian of that composition, that's the thing that turns, as a whole, x velocities into z velocities. I'm just, taking this little diagram of all these velocities are related in sort of three different ways. And you write those down as algebraic equations, and what you get is this. That the act of, just being a little inconsistent with my notation here, the act of doing JG followed by JF is, well, in fact, equivalent to the act of doing the Jacobian of the composition. And so you can see right here in how that, I think pretty natural, again, taking this new point of view on Jacobians as relating velocities, input velocities and output velocities. It makes this sort of this idea of viewing the Jacobian as a product of individual Jacobians. Well, yeah, of course it should be. I mean, what else would it be? If you're thinking of Jacobians, as I argue here, as a relationship between input velocities and output velocities. Okay, so look, I've given y'all a huge amount of sort of new points of view and concepts to digest, and I'm well aware that I'm shoving ideas into your intellectual mouth faster than you can chew and swallow them, right? So take some time. Make sure to chew on all of this and swallow, digest, right? Make sure that you get comfortable with these ideas. And you're going to have to do some sort of self-thinking outside of class. Okay. All right. Let me pause real quick. Let me pause for questions. Does anybody have any questions about this or this stuff here? Everybody good? All right. Okay, so let's talk about second derivatives. Do y'all remember the second derivative chain rule in single variable calculus? I'll bet you don't. I'll bet you never seen one. I never saw one. They don't do it that way, right? The point is, if you want to take a second derivative with the chain rule, okay, take one derivative with the chain rule. And then when you're done with that, take another derivative with the chain rule if necessary, right? So there's no need to write out a single separate rule that will do that for you. So likewise here, we're not going to have a second derivative chain rule, but what's awkward is there is some weirdness in how to apply the chain rule after you've taken one derivative already. It's just a couple of landmines. I just need to point out to y'all where the landmines are. And then the punchline is going to be, if you want to do a second derivative, if the chain rule if you're looking at a composition in some sense, just heads up, use the chain rule again. And don't step on the landmines. Okay, so let's start with an example. And in fact, really, I'm just going to explain by example on this. I don't want to get general. This is a classical first example. It's extremely common to use this as a first example. Okay, so let's suppose z is a function of x and y. Let's suppose also that x and y are functions of r and theta. And you'll notice, by the way, those of you who have seen polar coordinates in the past, anybody? Show of hands, polar coordinates? Most. Great. Okay. So if you haven't seen polar coordinates, no sweat. You don't really need to see that point of view here. But this is just, if you have, this is just the polar coordinates conversion formulas. Okay. And let's suppose you want to know about the composition. Maybe you want to understand the partial of z with respect to r. Right? So you want to understand that partial derivative. And you notice you have two pathways through the intermediate variables, thus giving you two terms in the chain rule, right? Just like always. We have, if you will, therefore a couple of, partials of z with respect to x and y, using the colors the way we have in the past. Now we have the derivatives, partial derivatives of x and y with respect to r. So it's just plain old, just apply the chain rule. And then rewriting, recall that we have this choice of notation here, that I'm going to rewrite that partial derivative in sort of Newton-like notation, and likewise here. And then another observation, notice that, given that we have explicit formulas for x and y in terms of r and theta, I could just straight up compute these partial derivatives. No big. Everybody on board so far? Okay, so here's where the landmine shows up. You say you want to compute a second partial. Okay, so we're going to take our first partial, and we're going to take a partial of it. I'm going to take a partial of this with respect to r, seemingly no big deal. How do I take a partial of all of this stuff with respect to r? Specifically, how do I take a partial of zx with respect to r? Is that just zxr? Can I just write it like that as, it's just, take z, do its x partial, do its r partial, just write it like that. And I want to point out that, no, that makes no sense at all. You cannot write, and let me do this in red as a warning, the partial with respect to r of zx, you just can't write this down as zxr. Because that would suggest that z can be viewed as a function of x and r simultaneously. Right? And you just can't do that. I mean, here's where x is, here's where r is. If you want to view z as being a function of both x and r, well, now you're kind of viewing z as being a function of four separate input variables, but these are not independent variables. X and r relate to each other. Right? I shouldn't put a check mark there. I should put a couple of exclamation points and a concerned smiley face. Right? I need to practice on my emoticon drawing with pens.
Squiggly mouth is good.
Squiggly mouth? Oh, okay. Yeah, all right. So like that? Yeah. Okay. Yeah. Okay. Right. That would be a great thing for them to have up as a tool up here is emoticon, right? Emojis, whatever they call them. Yeah. So it doesn't make any sense, right? If you want to view, you can reasonably view z as a function of x and y because, those are independent variables and you can just view that as a function. You can view z as a function of r and theta because r and theta are independent variables and that's the composition function and that's fine. But this idea that this is a function of those is nonsense. Okay, so don't do that, please. It's completely nonsensical garbage. Okay, so how do we fix this? The big idea is to just recall where zx came from. This z, I need to do this in blue, sorry. This z here, blue, come on blue. This z is an expression involving x's and y's. What happens when you take a partial derivative of that with respect to x? Bear with me here. But if you take a function of x and y and take a partial with respect to x, you get another function of x and y. So critically, this thing here is a function of x and y, just like its predecessor was. So indicate thusly on your diagram. It's an easy little fix, and this is going to totally allow us to bypass that landmine. Zx is a function of x and y. By the way, likewise, so is zy, just like its predecessor. Zy is a function of x and y. And now we've got a diagram to work with. This diagram is going to be our guide, our informant of how to take partials with respect to r as we proceed here. All right, so here we go. To get this second partial, I'm going to literally look at the r partial of this previous r partial that we just got through computing. Just going to do an r partial of that thing. The r partial of this expression, off you go. Now, we've got our diagram to tell us what to do when. And just take it one step at a time. Don't try to do this too fast. Don't take these huge, I'm going to do 3 steps of algebra in my head all at once. Pause, right? Take a deep breath. Slow it down, one little micro step at a time. And first thing I'm going to observe is that the derivative of a sum is the sum of 2 individual derivatives. Right, like that. I'm going to observe that since I'm taking a partial with respect to r is my input variable. As a result, theta is to be viewed as constant. Therefore, cosine theta is a constant. That therefore factors right out. Right? I haven't gotten to the interpreting zx yet. I'm just writing the summation rule for derivatives. I'm factoring out a constant, as is my rule for derivatives. Yeah. You had a question?
Yeah, isn't what the 2 lines you have?
Yeah.
You have to expand the top one, even though it's very similar to the bottom because there's no r in it?
I'm not understanding your question. I'm sorry.
You have the partial r of the whole term.
Yep.
And when you do it out, kind of, you sort of have just the partial r.
Yeah. This is just you might say this is all Calc 1.
I know, right? Do you have to do that step? Or
yeah.
Leave it at
No, we really have to do this step because I can't identify where this object is on my diagram. It's not on my diagram. See what I'm saying?
Okay.
But having broken it down as I just did, now looking at this object, that is on my diagram. That's a partial derivative. I want to know the partial of that with respect to that, and now my diagram can tell me exactly how to deal with that.
Okay.
Yeah, that's a great question. Yeah, absolutely. Everybody on board so far? And now, just do exactly what the chain rule tells you to do. The chain rule says that here we have a composition, partial of a composition. The chain rule says you get these 2 terms. There's the, if you will, there's the x term. And there's the, if you will, the y term. That's plain old chain rule. Just be careful. Right? Likewise for for this this factor here, that's the partial of zy with respect to r. And again, so that's going to, chain rule tells me I get this because, again, there's an x term and there's a y term. That's just a chain rule. Nothing fishy there. Right? And now you've got another thing that you can start sort of playing with, like in the same way that, after we wrote down the chain rule up here, then we could sort of, let's rewrite that in a convenient way. Let's compute that, capitalizing what we know about x. You can sort of start rewriting. And the rewriting is no big deal. The partial of zx with respect to x, that's just dxx. That's a plain old second partial. There's no composition inside of there at all. Z is immediately a function of x. There's nothing to expand through intermediate variables. Partial of x with respect to r. Oh, that's still cosine theta. That's nice. And don't forget about this factor out here. That's just computation. Et cetera, et cetera. This is that, and blah, 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 all the way on down the line, a bunch of analogous simplifications. And then it's kind of all over, but the algebraic, spiking of the football. How would we like to write this most conveniently? And you kind of notice that these two terms look exactly alike, and so let's rewrite like that. That's a little bit convenient. Okay. So there you go. That's how you compute the second partial with respect to r. So the big headline: slowly and carefully. And don't forget to identify, when you once you've done your first partial, don't forget to identify when you have in fact created new variables in effect whose partials need to be interpreted by the chain rule. Okay. All right. So there's some homework exercises on this, as I recall. I think same setup. I think they asked for you to compute the second partial of z with respect to theta twice. Analogous. The product rule is going to be a little weirder. Here the product rule was convenient. The product rule just this is a product, but one of them is a constant, and so it just factors out. So you're going to have to actually use the product rule in the theta calculation. So the single variable calculus is a little different, but everything else is morally analogous. Okay. All right. Okay, so the last thing we're going to talk about in the chain rule. By the way, chain rule is a big section. It takes a long time to get through the chain rule stuff. I want to talk about the implicit function theorem. This is a topic of single variable calculus that is usually, possibly even completely ignored in single variable calculus classes. It's at least undersold in single variable calculus classes. And it's undersold because in the single variable calculus class, you just don't have the tools. You don't have those tools yet to be able to give even a reasonable discussion of it. So this is going to look like we're revisiting a single variable calculus topic, and really it's not. We're now. I want you to think of this as we are for the first time giving a reasonable multivariable calculus consideration of a question which ultimately kind of should have been viewed as a multivariable calculus problem, but it kind of needs to be brought up in single variable calculus classes. It's a weird topic. Okay, so here's the question. Suppose you have a function of which you're looking at a level set. Now again, reminder, context, think about which construction. We are not looking at the graph of this capital F function. Please don't even think about the graph of this capital F function. Okay, so we're looking at a level set, and this level set then is going to be some curve, and I'm going to ask now a reasonable question, which is, okay, at a certain point, depending on where I am, locally nearby, if I would like to choose to reconceive of this curve, if I no longer want to think of this curve as being a level set, can I instead, this is the big question, can I view this instead as a graph? Can I view, for example, y as being a function of x? And I'm going to show you a couple of ways that this question might play out, depending on the point you're looking at. So, for example, let's suppose you're looking at this point down here, and notice I mean locally. So, obviously, I don't mean the whole curve, but just nearby this point. Can I view this part of the curve as being a graph? And the answer is, yeah, sure, no sweat. Look at this. That little piece of curve that passes the vertical line test, no problem. I can view that curve as being a graph of some function. It's not capital F, of course. Capital F is two input variables. The graph would be a surface, 3 dimensions. We're not at all talking about graphs of capital F. But this curve, this level set of F, could be viewed as a graph of a different function. Yeah. Okay, but notice, beware, that depending on what point you're looking at, this might simply not work. Let's look at that point right there. Near that point, even if I look at just the smallest little piece of that curve, near that point, can I view that little piece of curve as being a graph of something? And I'm sorry, the answer is just no. It doesn't even matter in this case, as I have it drawn here, how little of the curve you look at. It's always going to fail the vertical line test. And so, no, you cannot view y as a function of x. This is not a graph in that sense, near that point. Okay, so this is a hard question to deal with, and the answer, the way we resolve this matter, is called the implicit function theorem. And again, it's usually ignored in single variable calculus classes, and if it's not ignored, it's at least undertreated. So I'm not going to give you a rigorous argument here. We don't have time, but I want you all to walk away from this discussion with a reasonable intuition for why the theorem does what it does, and it's just a matter of looking at this picture and asking about what went wrong at this point, where you really can't do it. I mean, this little piece of curve, you can't view it as a graph, at least not in the y sense, right? And the reason why, bear with me, I'm going to be a little sloppy here, but it's because the curve is wrapping under itself. Right? It was over there, and then it kind of doubled back, and now it's over here, and that's why it fails the vertical line test. Specifically, it is doing that. It is making the moment where it wraps under is that point where, well, deeply connected is the fact that the tangent line is vertical. The curve has a vertical tangent line. Yeah. And then I'm just going to make the observation that I can reinterpret what it means for the curve to have a vertical tangent line. If the tangent line is vertical, this is vertical, and therefore this means in the y direction. The curve in the first place is a level set of f. This is therefore where f is a constant, right? Level set of f. That means f is constant, aka f is not changing. And so, look, if you just kind of say the words in a slightly different way, okay, you could say the curve is a vertical tangent line, or you could instead say that the function is not changing as you're moving in the y direction. It's just a rephrase of how to interpret that picture. So specifically then, this partial derivative is 0. Okay, so now how do we turn this into a theorem? We're going to turn this into a theorem by turning this statement around with what we call the contrapositive. If you have a problem, that partial derivative is 0. The contrapositive then says, okay, well, if the partial derivative is not 0, no problem. You all comfortable with the contrapositive? If A implies B, okay, well, then if you were to encounter a scenario where B is false, then A has to be false. Right? I mean, if you encounter a case where B is false, A couldn't be true. If A were true, that would mean B would have to be true, but we are assuming B is false. So anyway, the contrapositive is a really neat trick of logic, how to rephrase statements, and the contrapositive of this statement is that statement, and this is going to be our theorem here's an easy algebraic check from which we can conclude that there's no problem, and yes, I can reinterpret my level set locally as a graph. Yes?
Why f is not changing in y direction?
Yeah, f is not changing because this curve here is a level set. If you're staying on that curve, if you're moving along that curve, the assumption is that means that f is constant, and constant means not changing.
So f is a level set.
That's right. That was our sort of initial thing here. F is a level set. Correction. We are looking at a level set of f. Yeah. Okay. All right. Now, let me show you where this gets. Oh, yeah. Real quick. Yeah.
Why is it important or not important, but useful to observe
when something's a function?
Yeah.
Yeah. So the example I want to show you will totally answer that question. So here's a calculation that I think you've probably all seen in a high school single variable or whichever single variable calculus class you may have taken. Let's find the slope of the tangent line to, oh man, time flies. Slope of the tangent line to this curve, x squared plus y squared is equal to 25 at a certain point at 3, 4. So there's a point on a curve. We want to find a slope of a tangent line to a curve, and you're thinking, okay, so that means the derivative. But specifically, then, what I need is I need dy dx. Right? Here's the awkward part. Notice y is not given as a function of x. Right? Y is given as an input variable, not an output variable. So I very importantly, I'm not asking for the partial of f with respect to x. I'm asking for the derivative of y, reconceived of as a function with respect to x. So, can you do that? Is this a thing? Right? Well, here's what. Okay, now again, this always gets swept under the rug in Calc 1 classes, but here's how it gets done: is they say, well, let's take the derivative of this whole thing with respect to x. And so we get 2x plus 2y dy dx is equal to 0. And, not a second thought is given. But notice, I just assumed that y could be viewed as a function of x in doing this. I'm assuming that y is a function of x. It isn't always. See what I'm saying? So the very first step, in the evaluate, you try to find dy dx, and here, dy dx is it ends up being negative x over y is the formula that you would get in this argument. This entire formula is suspect because I'm assuming something that is really not obviously true, and in fact is sometimes obviously not true. Right? And look, mathematicians are real weird about making sure that what they write down is actually true. Right? So if your reasoning is based on a false assumption, you just can't do that. Okay. Now the observation is sometimes made that you look at this example and where would y not be a function of x? Well, y would fail to be a function of x at a point like that, at which point y would equal to 0, in which point this expression would explode in a fiery ball of death anyway. So, who cares? This is a common point of view. Again, mathematicians, we're not cool with that. It is not okay. Invalid reasoning is simply not okay just because, victimless crime. Right? It would explode anyway. It's just not okay. And by the way, this punchline does not always explode. So this is just a bad example. Okay, so we have to make sure that we're taking the derivative of something that actually is a function before we just go around pretending that we can take a derivative of it. Remember, you cannot take a derivative of a bicycle. Okay? You can only take derivatives of functions. If it's not a function, I don't know what you're talking about. And if y is not a function, it's more like a bicycle than a function, you cannot take a derivative of it. Okay. All right. So a proper development of this problem would be to say, step one, let's look at the partial of f with respect to y. Let's compute that partial of f with respect to y. Let's confirm that it's not 0. And it will be not 0 at all of these points here. It'll be, not 0 here and here and here and here. And then we can therefore conclude that this is valid. This argument here is valid for all the points except where y is equal to 0. And then the argument's fine. Okay. So, the multivariable version of this in the next minute and a half. Given a level set, so keep in mind now here I'm looking at a level set of capital F. We're not talking about a graph of F. Forget about the graph of F, not in play. If I have a surface that's described as a level set, can I ask with great concern, can I choose to view one of these input variables as itself being a function of the others, even though the algebra gives no reason to think that this is okay? Can I get away with just asserting that z is a function of x and y? And the answer is, well, most of the time. It's just that something might go wrong sometimes. Points like this, you're going to have a problem. The problem at that point is that, well, the surface is kind of wrapping under itself. How is it possible that the surface is wrapping under itself at that point? Well, the problem ultimately is that it's the surface is kind of vertical there. So, said differently, it's got a vertical tangent plane. And that means that as you move in the z direction, oh, I'm sorry, I have the wrong color there. As you move in the z direction, namely as you move along that plane, moving vertically, in other words, as you take a partial with respect to z, you're staying on the surface where f is constant because, of course, we're looking at a level set of f. So f is constant. Oh, let me zoom out. So that's the big idea. And again, you flip it around with the contrapositive. Problem means the partial is 0. And therefore, if the partial is not 0, no problem. Okay, this makes for a good place to stop. I'll show you some algebraic calculations you can do as a consequence of this next time. See you later. Have a great weekend. Don't forget about the exam on Wednesday.
That's possible.